Hey guys, today we're going to be talking about the concept of optimization in calculus. Specifically, we're going to use a very good example that's going to demonstrate what exactly you can do to utilize the strategy of optimization. So our example is a poster of area 6,000 square centimeters has blank margins of 10 centimeters wide on the top and bottom and 6 centimeters wide on the sides. Find the dimensions that maximize the printed area. Okay, so something that your math teacher probably told you is that you should always set up an equation first. In this case, we know it's a poster, right? So it has an x and a y dimension. And it gives us that the area is 6,000 square centimeters. All right, so we got that down, right? Okay. In this case, though, at the end, I don't think that we're going to be able to have a y in the equation. We want to get it down to one variable, right? So in this case, how would we put y in terms of x? Well, we could say that y is 6,000 over x. So just keep that in mind, okay? That y is 6,000 over x. We're just doing that because we want to get one variable. And that's x in terms of x only. But at the same time, we need to account for the margins. So it's 10 meters wide on both sides, on the top and the bottom. That means that we're going to have, in this case, we're going to have the little excess of 10 and 10, plus the x that's originally there, our actual dimensions that are printed, equals x plus 20. And then in this case, it's 6 plus 6 for y, for our actual printed dimensions of y. So that's y plus 12. So our total area is actually going to be, in this case, x plus 20 times y plus 12 equals 6,000. In this case, actually, we're going to write area, and we'll get to the 6,000 later. But let me just clarify, x plus 20, that's right, what we're going to do next. So like I said earlier, to ultimately solve this equation, we're not going to be able to have a y in. So what we'll do instead is substitute x in for y, and that means x plus 20 plus 20 plus 6,000 over x plus 12 equals a. So if we eventually multiply this out, we're going to get the equation a equals 6,240 plus 12x plus 120,000 over x. Now, if you're confused about how to get there, you can just pause the video, and I'm sure you'll be able to do the algebra to figure it out, but this is ultimately what you're going to get for A once it's simplified. So what the max area, however, is in this case, I want you to think about, if once we have this equation, what sort of graph this is going to produce. So I'll let you pause. I'll pause for a moment and let you think about it now. Anyways, I'm going to show you now what I think it would be. In this case, I'm going to assume this looks kind of like a quadratic, doesn't it? So it's going to look kind of like a parabola. The maximized dimensions. In this case, this is going to be the maximum length or x dimension that we want. And it's going to increase at a certain point here. But how would we find this sort of point where the max is? Well, I'll give you a few seconds to think about it now. But since you've been studying calculus, you might notice that out here, I'll give you a zoomed in look, our parabola sort of just flattens out. So when we know that our parabola is flat here, for this little moment here, the rate of change is going to be 0, right? And when the rate of change is 0, what do we say that is in terms of an equation? This is where the calculus comes into play. We say that the derivative of a over d over x is going to be 0. So we know that area prime is 0. So once we know that area prime is 0, but we know from our taking the derivative of area here, so if we just do, in this case, derivative of area, so we take a prime, we're going to get the equation 12 minus 12,000 or 12 minus 120,000, I meant to say, over x squared. So since we know that the derivative is going to equal 0, and in this case the derivative is also going to equal 12 minus 120,000 over x, we can set these two equations equal to each other. Okay? So 12 minus 120,000 over x squared equals a prime, which is equal to 0. Okay? So once we do that, we're able to do this pretty straightforward. Okay? So we can just say that 120,000 over x squared is equal to 12. Then we can say 12x squared is equal to 120k. And once we do that, it becomes pretty simple. We know that x squared is equal to 10,000, okay? And x is the square root of 10,000, and that's going to be 100 centimeters. So we have one of our dimensions too, and that's 100 centimeters. That's going to be the printed area. Of course, I'll just say that y we know from way back earlier is going to be 6,000 over x. So that's 6,000 over 100, so that's 60 centimeters. Okay, anyways, so now that we have our printed dimensions, I'll write that down here, is going to be 100 times 60. What does that make our overall dimensions? Well, that's pretty easy. We just add 10 on both sides. So 100 plus 10 is equal to 120 centimeters. So that's our dimensions for length, in this case x. And for width, we're going to just add 6 and 6 to y. So that's 60 plus 6 is equal to 72. Okay, so we know that our final dimensions are 120 by 72 centimeters. So I'm just going to give a quick overview of how exactly we got there and how you can apply this concept of optimization to future calculus problems. So the first thing we did is set up an equation here. You can see that our equation was, our original equation was x times y is equal to our area, but we were able to broaden that and separate that into printed and total area. In this case, we needed to add 10 centimeters on each side, so that's x plus 20 and y plus 12. And we know that y is 6,000 over x in our original equation. So we substituted that into our area equation, and we found out that a is equal to 6,240 plus 12x plus 120,000 over x. Now, we sort of thought about this in our head and thought that, yeah, it's going to be a parabola, this equation, so we can find where the ideal part is, where it's highest, because that coincides when the rate of change is 0 and the parabola is flat. So once we're able to say that the rate of change is 0, we can say the derivative of area, in this case a prime, is equal to 0. But we also know at the same time, just through our rules of derivatives, that a prime is equal to 12 minus 120,000 over x. So once we know these two things here, these two equations for derivatives, we're able to set them equal to each other. Once we do that, it's pretty straightforward. You just plug and chug, and eventually we get our first dimension that is only printed area. X is equal to 100 centimeters. Substitute that back into our equation for y, we get 60 centimeters. add in the little side areas, 10 centimeters on both sides, you get a total of 120 centimeters. And for y, add 6 on both sides, you get 72. So our final dimensions are 120 by 72 centimeters. Now I hope that you found this video helpful. Just remember that you need to sort of think about where something flattens out or how you can use derivatives and combine two equations in one to optimize your situation. Thanks for watching.